So now that I have explained to you what are general circulation models, and now that we've built up some confidence that these models are sound, let's look at what these models tell us about the future. Let's look at projected climate change. What you're looking at here are results for the global mean surface air temperature. There's 42 models, not 30 as I said recently. And what you see here in black is the observed global mean surface air temperature, and then in the gray area you see again the reconstruction by these models of the past. And as I said before, they do a reasonable job. So given that they do a reasonable job in the past, let's look at what these models tell us in the future. Now, what happens in the future depends, of course, not only about what do these climate models tell us, but also what are our expectations for future emissions. And that is what you see in the different colors. And that's the four basic scenarios that you see here. One where there's a very stringent climate policy, and one where there is no climate policy whatsoever. Emissions are very high in RCP 8.5, emissions are very low in RCP 2.6. And that, of course, drives a wedge in our future projections. Now, depending on the model and depending on the emission scenario, by the end of the century, and for many of the listeners, this is by the end of your lifetime, the world could perhaps be 1, maybe half a degree warmer than it is today, but it could also be 5.5, 6 degrees warmer than it is today. That is simply the uncertainty we will have to live with. And the answer to the question, how warm will it be in the future, depends on two things. One, which model do you think is most credible, but of course also on how high will our future emissions be. That makes a big difference, and that's actually a bigger difference than the difference in the models. Now, you may think that 5.5, 6 degrees of warming is pretty hot by the end of the century, but of course if we don't do anything about our greenhouse gas emissions, if we just keep on burning fossil fuels, then by the end of the 21st century it will get hotter still. Actually, the graph here is cut off at 12 degrees, but it goes up to 13 or 14 degrees. That is if we keep on burning fossil fuels. If we don't, we keep the temperature well in check. Now, this is what would happen at the global average. It's not particularly interesting. What you're looking at here is the spatial pattern of warming. There's a lot of maps here. From top to bottom, emissions increase, so low emissions at the top, high emissions at the bottom. And then if you move from left to right, you see you're moving further in time. So this is by the middle of the century, this is by the end of the century, and this is by the end of the next century. And what you see is two things that are immediately obvious. If you move further out in time, it gets hotter, just like it did here. Also, if emissions are higher, it gets hotter, just like it did here. So those are the two primary signals, but you see other things as well. One thing that you notice is that the poles increase faster than the tropics, and this is to do with the physics of the system. The polar regions would be expect to warm up faster than the equatorial regions. Second thing that you notice is that the land warms faster than the ocean. Again, basic physics, the heat capacity of water is much higher than the heat capacity of soil, and therefore you would expect the land to warm faster than the ocean. This, of course, matters to humans because most humans live on land rather than on water. The things that you do not see in this graph is that winters are expected to warm faster than summers, and nights are expected to warm faster than days. So the pattern of warming is by no means uniform in any dimension, but what we can, and it's of course very uncertain how much the planet will warm, as you can see in these graphs, but the signal is pretty clear. There's only one exception here, and that is in the shorter run at this area over the North Atlantic. We may actually see some cooling there that has to do with the realignment of ocean currents. But by and large, you can say, well, it's going to warm everywhere. We don't know by quite how much, but we know it's going to warm. We know it's going to warm more over land than over the ocean. We know it's going to warm more in winter than in summer. We know it's going to warm more towards in higher latitudes than on lower latitudes. So all these things are pretty clear, although we do not know the exact extent of the warming, of course. That picture changes completely if we look at rainfall. Again, a lot of maps. This is a different set of maps. It's all for one scenario, so emissions are the same everywhere. Again, if you move from left to right, we're moving at further in time, mid-century, end of the century, end of next century. But now if we move from top to bottom, we're looking at the boreal winter, spring, summer, and fall. So this is a different seasonal pattern. In blue, you're looking at places and times where it gets wetter. In the brown, the yellow, and the red, you're looking at places where it will get drier. And you see very distinct spatial patterns here. One thing to notice is that if we focus on where we live, then actually what you see then in winter it is projected to get wetter, it is blue, but in summer it is projected to get drier, it is brown. So people who go on television and say, well, because of climate change we will get more floods and more droughts, they're not talking nonsense. They don't have a hole in their head. What they mean is we will see more floods in winter and we will see more droughts in summer. And that is a perfectly consistent message. You see other patterns as well. Again, what you notice is that there is a different pattern over the higher latitudes than over the mid latitudes, and particularly what you see here, but it's true over the northern hemisphere as well, is that there's a general shift of rainfall from the mid latitudes towards the higher latitudes. Now that is not so much an issue in the northern hemisphere, but it is a big issue in the southern hemisphere. Essentially what the models project is that the rains that are currently falling over southern Africa, those rains in the future will fall over the Southern Ocean. That the fish don't care, but the farmers do. It's not that it's going to rain less, it's just that the rain will fall on places where we cannot grow crops. And this is a problem for the food supply. The final thing I want to say about this graph, what you see is a very rich pattern. Depending on the time of year, depending on where you are, it may get drier, it may get wetter. The thing that I haven't explained, because it was not relevant for the previous graph, in the previous slide, in the dotted areas, there is model agreement. That is, all 42 or 39 models in this case roughly agree, or at least on the sign of change. In the dashed areas, there is actually no agreement between models on the sign of change. The map shows the average across models, but that of course does not mean that all these models show the same response. And unfortunately, what you see is that those dashed areas are actually quite extensive. We can be sure that in Siberia in winter it will rain more. That is pretty clear, and all models will tell you that. But if you focus, say, on the Horn of Africa, some models say it will get better, some models say it will get drier, and it's actually pretty unclear what the sign of change will be. Basic physics tells you that if the temperature changes and if temperature gradients change, that is the land warms faster than the ocean, then if temperature gradients change, then wind patterns must change, pressure patterns must change, wind patterns must change. Um, Basic physics tell you that if it gets warmer, then the air can contain more water vapor, and water on the surface evaporates faster. All those things are pretty clear. So if the temperature changes, then rainfall must change as well. That is pretty clear. Rainfall will not stay the same, but models actually cannot agree, even in many places on the planet, on the sign of that particular change. And that is, of course, a big problem for those who want to anticipate future climate change and do something about it. Besides temperature and rainfall, there is also sea level rise. There's a lot of confusion over sea level rise. Most people think about climate change, well, the planet's going to warm, and it means that snow melts faster, and that means that ice melts, and therefore the sea level will go up. That is true, but it's true only to a very limited extent. What is much more important, that if the atmosphere warms, then the ocean must warm as well, because it's in direct contact with the air. And if water expands, if water warms up, it expands. Now, that is something that people have difficulty imagining. And if you take a cup of tea, and at the starting point it's 100 degrees almost, and then you let it cool down until it's a drinkable temperature, and your cup of tea hasn't shrunk. It's not that you have less tea when it cools down. It's actually not true. It cools down and therefore it shrinks, but only by a tiny little bit, which just is not noticeable. This is something that you learn in school that happens, but you actually cannot really see it. So why, if the ocean would warm by a few degrees, rather than from 100 degrees almost to 20 degrees of drinkable temperature, or 40 degrees of drinkable temperature, there's a much larger gap, and it doesn't visibly shrink. So how can it, if the ocean warms by a few degrees, it leads to substantial sea level rise? The answer to that question is that, yeah, the ocean doesn't expand a lot, but the ocean is very, very deep. On average, the ocean is 3 kilometers deep. And that means that it only needs to expand by 0.1% to have 3 meters of sea level rise. And 3 meters of sea level rise on a human scale is actually quite a lot. It's almost twice the average height of a human. So a tiny expansion of a large column of water leads to a noticeable, to humans, change in sea level. Projected sea level by the end of the century is somewhere between 30 centimeters and 100 centimeters, almost a meter, again depending on the scenario and depending on the model that you're using. And that is noticeable, that a meter sea level rise over this period can be seen. Again, the pattern is not uniform over the planet. There's parts of the world that where the sea level increases faster than in other places. Sea level rise is not the last effect of climate change that we need to worry about. There's also change in storms. Again, if temperature changes, and temperature changes differently in different places, the pressure patterns will change, and that means that the wind will blow differently. So that is pretty clear. What people often worry about with climate change is what it will do to storms, both tropical storms and extratropical storms. And the news there is not good. What models have found is that if we focus on hurricanes and those sort of things, then it will not be the case that there will be tropical storms in places where there are currently no tropical storms. There won't be a hurricane that hits London. That is very unlikely. So there's no change in area. There's probably also no change in the frequency of tropical storms. They will not occur more often. And it may even be that they will be less frequent, they will occur less often, but these storms will probably get more intense, they will become more violent. And this matters, and this is actually the wrong news from a human perspective, because the damage done by storms is actually slightly less than linear in their frequency. That is, if a storm hits you and then a second storm hits you a little bit later, then all the vulnerable stuff has been blown away in the first storm. So the second storm actually does less damage than the first storm. So we don't worry so much about, we would not worry so much about an increase in the frequency of storms. But the intensity of the storm matters, and that is because the force that wind exerts on your building or on your trees, on your wherever, is the wind speed to the power 3. Force is wind speed cubed. And that means that if the storm becomes more violent, that is, wind speed increases, then the damage that is done actually increases with the third power. So it goes up very, very rapidly. Now that is true for tropical storms. It's unfortunately also true for extratropical storms. That as far as we currently understand the systems, those storms will become more intense. The maximum wind speed will go up. The highest wind gust will be stronger. And that is something to worry about. I talked about rainfall. There's one other aspect of climate change that should not be overlooked, and that is ocean acidification. Why is this an issue? In the olden times, when people talked about carbon dioxide, they didn't call it CO2, but they called it carbonic acid. Now, there's a disagreement whether carbonic acid is any CO2 or CO2 dissolved in water, but the crucial term here is acid. CO2 is a mild acid. Now, by the laws of partial pressure, if there's more CO2 in the atmosphere, that is a reason for concern about climate change, then there must also be more CO2 in any water that is in contact with that atmosphere. Part of the CO2 is taken up by the ocean, it dissolves there, and because it's an acid, it makes seawater less alkaline or more acidic. Now, why is this a concern? If you take a shower, what you notice is that after your shower there is this white residue in your shower, and that white residue is the calcium that came with the water, and the water evaporates, but the calcium remains behind. Now, if you want to clean your bathroom, and rumor has that some students actually do this occasionally, you want to clean your bathroom, what do? Well, you go to the supermarket, you look at all the cleaning products, and all those that are used for cleaning kitchens or cleaning bathrooms have acid in. And the reason for that is that the way to get rid of that white residue, the calcium, is to pour on acid. That is how you clean your bathroom. You pour acid on your surfaces. Now, why is this an issue? Well, if seawater is more acidic, it dissolves calcium. It's not so much a problem for animals like ourselves. We have our skeleton on the inside of our body. Skeleton, recall, is made of calcium, and it's absolutely no problem for you to swim in slightly more acidic water. It's not that the water will get so acidic that it will actually hurt your skin. No, it would dissolve your skeleton, but it cannot reach your skeleton. But there's also other animals that have the skeleton on the outside of their body. Mollusks, lobsters, a lot of species of plankton, coral, and so on and so forth. They have the skeleton on the outside of their body, and those type of animals will be in trouble because it will be harder to grow, it will be harder to maintain their skeleton, it will be harder for these animals to reproduce. And then, of course, that is a problem for everything that feeds on those animals, or for everything that feeds on those animals that feed on those animals. right? So this is an issue. At the moment, it's a bit unclear how big of a problem ocean acidification is, because quantification has proven hard, but it's not a problem that should be neglected.